All of you can see my screen.
Yes, sir.
Okay, okay. Okay. Can you see my OneNote, everybody?
Yes, sir.
Okay. So today's talk is on swarm algorithms theory and practice, and the outline of the talk is based on these 5 points. And this is just overall outline, but we will be going deep into that. We will first see gradient methods and its limitations, then NFL theorems, then function types and examples, PSO intuition, and we will type in the first PSO code today. Okay. These uh, things, equations that I've written, are some artificial functions that are used in the field of optimization. Okay. So I'm going to deal today on a functional basis of optimization. Okay. So, okay, let us begin with the classical algorithms and the problems with classical algorithms. Okay. The gradient descent is perhaps the most well-known algorithm for optimizing, and it was introduced by the mathematician Cauchy. The algorithm by itself is very simple, and it uses the gradient of the function to optimize it. Let us assume that we have a function defined by two corner points. I'll call this as x-min, and, and this one is x max. Our primary interest is to find an optimum or minimum point, that is this one. The x star would represent the minimum, global minimum in this case. Okay, how do we achieve that? Yeah, so we should search for the minimum. Okay, and Cauchy's algorithm states that you start at some point, say any point, okay, between x min and x max, and he assumed that there are certain things about the function. The function is unimodal. F is unimodal, meaning it has only one minima and there are no other minima, and it is differentiable everywhere. Cauchy's algorithm goes by this formula that x of n plus 1 equals x of n plus eta df by dx at x of n. Let us say that our point x of 0 is this. So we need to find out the next point x of 1. Okay. So x of 1 would be x of 0 plus eta. Eta should be a small number. This eta is called as learning rate parameter. We will not worry about eta for the time being, but eta is small. Let us say eta is 0.001. Okay. Generally, eta is chosen to be small, and we will see that why. Okay. And we are starting from x0 and our x1, the next point, we have to find out based on this algorithm, that is this equation. Okay. Our x1 is, sorry, it should be minus here. Now we go to the, we find the slope. What is the slope here for x0? It turns out to be a negative number. The slope at this particular point is a negative number, negative slope. So when you multiply with eta, it will become, so overall df by dx is negative, and you multiply with eta, you will step closer to the minima by moving. Your x1 will be located here. If this is x0, we will advance 1 point ahead, little bit, to x1. Because the slope is negative, and you multiply with, if you use this algorithm, the slope is negative, and eta is and you have one more negative sign here. Negative into negative is positive. So from x0 to x1, you advance from left to right. Okay. In the next step, x2, you once again you start from x1, then you take eta df by dx, and dx is evaluated at x1. Okay. So now you take this slope, which will be, this slope might not be the same as x0, but it will be somewhat lower. Okay. So the slope will be somewhat not so steep, but it's somewhat less steep. So your x2 will be an advancement from left to right. So you will end up somewhere here, x2. So if you keep on iterating this process, you will eventually reach x star. Yeah. So we have to take a lot of care. This algorithm, which was invented by Cauchy some 200 years back, is called as gradient descent. Okay. This is a very nice algorithm to find the minimum, provided the function is unimodal and it is differentiable everywhere. Okay. We can see what happens if eta is, I suggested that eta is small. What if eta is large? Let us say eta is 100. Now let us see what happens. If eta is 100 and you start from that particular point, actually you still move from left to right, but your movement will be a giant step. You will overshoot x star and you will go somewhere here. So your x1, instead of lying close to x0, it will be a giant overshoot, and your x1 will lie here. And your x2 will further overshoot because the slope is positive, and you have to go negative this time. So your x2 will go away. Okay. So this is not a good idea. So x eta around 100 is bad. Learning rate parameter is too big, so it is bad. Learning rate parameter eta equals 0.001 is too small, but okay. Let us consider some other learning rate parameter, say eta equals 0.1. This time, so we apply the Cauchy formula, this formula, That is x1. We use this formula. This time the slope is positive, so you will advance from left to right, as we had seen. So, but you will go, your landing place will be somewhere here, which is, this will be our x1. And this is not a bad landing place. And if you apply the Cauchy algorithm one more time, okay, now it will no longer be plus, it will be minus for x2. Because the slope is positive and eta is also positive, when you multiply these two quantities, you have to go right, from right to left. Your advancement will be from right to left. So our new x2 will be here. Okay. So as iteration passes by, you will hit both the sides, and at very large iteration, you will eventually reach the minimum. This gradient descent algorithm is also referred to as had been used for quite a long time, okay, until the heuristics had come into picture. This is only reviewing. Maybe most of you know this gradient descent. Okay. Heuristics have a different approach to solving these kind of problems. Okay. And there are many problems that gradient descent could not solve. The gradient descent is not useful when the function is multimodal. So if you have a function that has more than one minima, gradient descent cannot help you. Yeah. So let us see that you have more than one minima. So this is x, this is f of x. We have a function like this. Okay. And your starting point is here. So you'll never get to reach the minima, which is located here or here. You might end up to this minima. That may be okay if you are happy with the solution. That is okay. But these solutions are better solutions. Okay. We'll call it x1. x2 and x3 are better solutions. So f of x3 is less or more or less equal to f of x2, but it is definitely lower than f of x1. You're losing f by starting at this point. It can only search around here, and it will reach to f of x1, and the algorithm will give you x1, but it is not the optimal thing that we seek. Okay. So these things have a problem with multimodal functions, gradient descent, or other the class of gradient descent algorithms do not help us when there are more than one minima, unless you are able to have some picture about the function, and you choose the right location to begin with. Yeah. This is not guaranteed always. We don't know about the function. Since we don't know about the function, we need some kind of black box optimism. Okay. We may not know completely. We may have some information about the function, but not where the minimum is, the neighborhood of minimum is likely to be. Okay. So in this case, gradient descent does not help us much. Okay. The second condition that gradient descent applies is the function should be differentiable. It is not differentiable, then you have serious problems. Suppose you have a function This minima appears like this. So we have a function which appears like this. So this is our minima, and our function is under root of mod x, and say under root of mod x minus x0. And our minima is here. We are unable to reach that minima because at this particular point, minima itself, the function is non-differentiable. So there are many problems with these things. So we need to look at an algorithm which can handle these type of functions, the functions which are multimodal and the functions that are non-differentiable. Okay. So these things, we need a better algorithm. So I would like to display you some functions. Uh, okay, so okay. So these are some of the functions, but the functions we will be calling them as objective functions. The type of functions that we might have is the function could be unimodal, the function could be multimodal, the functions can be otherwise rotated multimodal functions. And there
Excuse
are
me, sir.
tell me, madam.
Participants, please mute yourself. Some background noise is there.
Okay.
Participants, please mute yourselves.
Okay. There are other special multimodal functions. Okay. We will see how these functions come into play. Okay. One of the common functions that we might want to show you is this sphere function, which comes very often in optimization. Yeah, this is a sphere function. It has minimum at 0, 0. And can you see my MATLAB screen?
Yes, sir.
Yes, sir.
Yeah, it is differentiable everywhere. You can rotate the function and see its different angle viewpoints. It is differentiable everywhere, and it is also having only one minimum. So this function serves as a benchmark function. Like this is an artificial function, but it is useful to apply our algorithms on certain artificial functions to prove our superiority of that algorithm on those functions. Okay. So this is, I'll show you one more example of the unimodal function. Yeah. This one is an elliptical function. It looks like an ellipse, and it also has one minima. Okay. This time it is a little trickier to note where the minima is lying, but the minima is at around 0, 0. So today we have a functional basis of optimization. So we assume that we know certain things about the function before we optimize it. This one is a very commonly used function to prove how competitive the algorithm is. This is called Rosenbrock function or banana function. Okay. This is a Rosenbrock function. It's actually some kind of weird kind of multimodal function. It's very difficult to locate its minima among all the functions. That this was a very difficult function to locate its minima. It has a long valley out of which you have one minima hidden somewhere in the valley. Okay. Now we will look at some multimodal functions that could be of interest to us because our primary goal is to solve multimodal functions. Since most of the uh, functions that we encounter in electrical engineering are multimodal type, we are primarily interested in these type of multimodal functions, and I will show you one of them now. Yeah. Okay, so we'll go to the next function. This maybe the range is too big for this. This is a common function called rastrigan. As you can see, it has a lot of more than multiple minimas. Okay. If you can see very clearly, can everyone see the landscape of this function, rastrigan? See, please note that it has multiple minima. It has multiple valleys. Okay. And locating the lowest valley is an extremely challenging task in the field of optimization. Any questions? Okay. So these are some of the competitive functions, and if our algorithm proves to be better in these functions, we assume that it will do well on the real time problems that we face. Okay. We would like to see one other function which is actually, yeah. This clearly shows that it has multimodal properties. Can you see my MATLAB figure?
No, sir.
Oh, okay. That is a problem. Can you see it now?
Yes, sir.
Yeah. Okay. See, as you can see in this picture, it has more than one minima. It is very evident, right? The minima are numerous, and the blue color which is located in the middle, is the lowest. It's called global minima. Other minima are local minima. So our objective in getting it is to get our primary objective in this optimization is to go to the global minima and somehow escape the local minima. The more successful we are in doing that, the better is our algorithm. Okay. So since we have to formalize our problem into an objective function. Whenever we have an electrical problem in the application, we would like to formulate it as a function that is having multiple dimensions. More that is dimension meaning the number of variables it has. Okay. Then you will be able to visualize the function in 2 dimensions case. If it has multiple dimensions, then you cannot visualize. But the idea in 2D carries up to n dimensions. Okay. So I will show you one more function. That is the last one. Okay. Okay. This function is called Weierstrass, and the Weierstrass function has it is continuous everywhere but differentiable nowhere. Okay. So you cannot take the derivative of this function anywhere, but it is continuous everywhere. It has some peculiar mathematical property, so it is considered to be very difficult to differentiate the function. And finding its minima is also extremely challenging. Okay, so we will get back to. So how does PSO achieve that? Finding minimum. Okay, let us say that we have a multimodal case. So we have a function like this, say. In swarm intelligence and other heuristic algorithms, we employ an army of points. We don't start with one point. We use many points. The points could land anywhere. The thick dots that I put are the points. Okay. So we use army of points. So our points could be located at many places. Okay. And our algorithms do not use gradient because we assume that the function is not differentiable. So even in this case, our algorithm should work. Okay. In swarm intelligence or particle swarm optimization, we locate among these points, all of them are called members of swarm. We call them as X. Each of these points are called as X. That is the particle. They represent the particle. Okay. And each of these points, they are initialized randomly between X-min and X-max. This is an one-dimensional case, dimension equal to 1. But the geometry is similar even for higher dimensions. Okay. So you put the points arbitrarily in the X space. That is, you put the points at arbitrary locations of X. Okay. And this X space, that is the region between X min and X max, is called as search space. This is search space. And the vertical regions of f of x, the values that f can take, all the allowable values of f, they are called as solution space. Okay. So these points have to move according to some specific rule. Okay. So what we do, we find out which one is the best, which point. I will call them x1, x2, x3, x4, and x5. We notice out of these 5 points, x5 is at the best position. Okay. We call x5 as the global best. X5 is our global best. Or simply G best. And we allow the particles to move about between X min and X max. The rule that we assign in particle swarm optimization algorithms is that we find something known as velocity. V equals V of n equals V of n minus 1 plus C1 R1 G minus X of X of n minus 1 plus C2 R2 P of X n minus 1 minus X of n minus 1. Okay. What this line says that we have a velocity term, and that velocity term has 3 components. This component is the previous velocity. So if the particle, each of the particles are allowed to move within the search space, and if in the previous case, if you had moved from left to right, x1 has moved from left to right, and it has reached a better position. In this case, yes, it has reached a better position. You allow the particle in the next iteration to move in the same direction. Okay. Like x1 has moved from the original position to this point, like x1 at 0 is here, x1 at 1 is what it has moved from left to right, and it has reached a better position. So you keep that velocity or the inertia the same. Okay. That is the first component, the velocity in velocity. The second component is, among all the points that you have, x5 is the global best. Okay. And x5 is also our G. So all particles will move towards the global best. Okay. I am asking all the particles to have one component of movement towards the global best. That is x5. I am asking all particles to move towards x5. x2 will also move towards x5. x3 will also move towards x5. x4 will also have a component moving towards x5. Okay. It may be better, it may be worse, but we don't know. We can only try that. And that is a heuristic intuition behind particle swarm optimization. And the third component that covers our second component. And the third component is that probably you move towards a personal best of the individual particle. X1 has been moving around over the search space, and if X1 has found that its best performance X1 has ever reached is only this, okay, it cannot reach any further. So you also try to move X1 towards the personal best, okay, its own best that has ever reached. Okay. Now, after finding out its velocity, we add that to our position x of n equals x of n minus 1, which is the previous point, plus v of n. So you keep on iterating this for all the particles. Okay. So we keep a track of the best historical best location. In this case, among the 5 particles, x5 has a historical best location, and that will be kept in the memory of particle swarm optimization algorithm. Okay, we will quickly see that in MATLAB. Okay. Okay. So we will uh, write the particle swarm optimization algorithm. So you need to define the search range, okay, between which limits you have to define the search limits. That is extremely important. You have to define what x min is. In this case, the search range minimum is minus 10, and we are going up to plus 10. It's extremely important to define our search ranges. And we also have to define our velocity ranges. V min equals x min. In our case, I'm choosing the velocity minimum and maximum to be same as the velocity, the search range maximum and minimum. It doesn't have to be so, yeah, but it is necessary to give a limit to velocity minimum and maximum. One thing you have to notice is the velocity minimum. Please take care that this should always be a negative number. Actually, many people, this is practically many people do this mistake. If the velocity minimum is not a negative number, okay, when you move around in the search space, you only move forward. You never move backwards. Okay. I'll show you this. So, okay, we will initialize the particles. So let us say take 100 particles. This is how you define the particles, and you are initializing that within the search space. So this is a command, or this is how you build the algorithm. This time, I'm going to write the code for a 30-dimensional function. So this is a random number generator which generates a random number having 30 rows and one column. So it's actually a vector. Any questions? You have to define your function. Okay. So we have defined our function. It's the sphere function in our case. The value of the function is called as the objective function cost. I'm evaluating the function for each point. So you can also initialize velocity. Can everyone see my MATLAB code? Okay. Can you see my MATLAB screen?
Yes, sir.
Okay. So velocity, we use the same algorithm step to initialize our velocity. So there you have the velocity. And I have chosen 100 particles within the search space. Okay. That is why it is for P 1:100. And I'm initializing all particles, each of them. In the previous example, I showed 5 particles, but in this MATLAB code, I am taking 100 particles. Okay. Now we initialize the personal test. The personal test has also to be introduced. They also have to be okay. Since the personal best will have a different cost, the evaluation of X will be different. So we have to initialize the costs as well. I'm indicating, see, this is P best, the vector, and the next particle P dot cost is the scalar, the evaluation of the function at that particular point. When you write this command, f equal to out of sphere, func equal to sphere, it means I'm asking the MATLAB wherever I use a command f of x, whenever I type f of x, it should evaluate sphere of x. Sphere is a different function that I have defined elsewhere. Okay. And I'm asking MATLAB to take sphere as my objective function. Okay. See, one other parameter that we look for is we need to keep track of the function evaluations. Every time we evaluate the function, we I am incrementing a variable. Okay. So every time I'm evaluating, I'm 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 calling the subroutine to evaluate the function. I have to keep track of the count. How many times I'm doing it. There is a reason for that, which I will explain later. So in this if loop, I want to check whether my particle cost is lower than the personal best, because personal best is supposed to be smaller than the particle cost. Okay. If personal best is not smaller than the particle cost, as this line has indicated, you have to update that as a particle best. Any questions at this stage? So the global best is a best of all of the points. So you need to define a global best. So that can be done. It's p equal to 1. So I'm initializing 100 points. And if p were 1, then g best is the global best is a particle best. And g best. Okay. So the idea is here, for every particle, we have defined 100 particles. Okay. Every particle, you have to find the cost of the point. Okay. So we have 100 particles, so 100 cost points. Okay. So this is an array. Particle p dot x, p takes a value from 1 to 100. Okay. So each x is a member of the swarm or a particle. Okay. And we have defined the velocity for each individual particle, and each individual particle has a personal best as described by this line. Okay. And each personal best has also a cost associated with it, that is represented by particle p best underscore c, okay, where I have evaluated the personal best. Okay. Every time I invoke a function, I have to give, I have to keep track of the count. Okay. Whenever I evaluate the function, why it is needed is actually whenever we try to evaluate the complexity of the algorithm, like how much time it will take, it turns out that evaluating the function or finding the value of the function at a particular point turns out to be the most expensive computational operation. Okay. So if you do it at a lower time, if your count is not too high, if you can reach the minima at a lower functional count, then you have written a better algorithm. Okay. So we have initialized a swarm with particles, personal best, and velocity, and their respective costs. Okay. So now we define the iteration. So we are iterating it multiple times. In this case, I have taken it to be 2,980 times. So we do the velocity calculation. So this is what I said earlier, like this is same as what I put in the paper, the one note. This is the initial term, particle p dot v. The next is the global best. But before doing that, you have to initialize these ones. Acceleration coefficients, take them to be 0.05. And you initialize two random numbers. It's the first line for the particle swarm optimization. This is what I put here. V of n minus 1, C1 R1, where C1 is the acceleration coefficient, C1 and C2 are acceleration coefficients. R1 and R2 are random numbers. In this case, our random numbers are generated between -1 and 1. So random numbers are generated uniformly between -1 and 1. Okay. And after finding out that velocity, you add it to the point. So if the velocity cannot, the limits has always be the velocity limit V min and V max must always be V min, as I said, must always be a negative number. And V max should be a positive number. You can choose to reduce the velocity or increase the velocity, but this condition must be maintained always. Otherwise, it will the point the swarm will move only one direction. It won't come back. It won't move in the reverse direction. Then you won't get any optimization. Or in other words, if you choose V min to be positive, all the points will be going from left to right, and none of the points will move from right to left. Yeah, in this case, moving from left to right seems to be the best option. But if all the points were initialized in some other location, say like this, let us say we have the function like this. So moving from left to right may be better for this point and maybe better for this point, but not for other points. Okay? It is not always the best option. Okay. So let us go back to the code. Okay. So now we go to the second step. Before going to the second step, you have to make sure if you are adding something to the velocity, and the velocity should not go out of the bounds. So you need to make sure that the particle does not go out of the bounds. So this is what you should do. Restricting the particle within the bounds. It's very clear. So the maximum that the particle can go, this command says it will take all the individual. This is a 30-dimension vector. And out of 30 dimensions, the maximum the particle can take is only v min. Okay, so none of the velocity vectors component can exceed can get lower than v min. So this effectively makes sure that your velocity vectors are within the bounds. Okay. So now we add particle e dot x equals particle e dot x plus particle e dot p. Since we are primarily interested in locating our minimum between uh, the bounds, we once again have to apply the bounds condition here. So we need to restrict the particle between the bounds. This time I have to apply x min. And now this time it is similar to what we did for velocity. We are doing for the particle x. We are restricting the particle within the bounds. Okay. So we evaluate the function, new function, particle p dot cost, because we have located a new point, and we want to see if the new point is helpful in our search. We want to see if the new point, that the new location, particle p dot x, has found out anything new. So if particle dot cost were lower than the personal best, you initialize the personal best. Okay. The new found particle location, the cost is compared with the personal best, and if the personal best is found to be, and if the new found cost is better than the personal best, then you update the personal best, and you once again compare that with if particle. You also have to compare the particle best. Uh, Now you have updated P best. You compare the P best with the global best, G best. If the particle P best cost were lower than the G best, then you update the global best. So by repeatedly doing it for 2980 times, we should reach a minimum. Okay. So we'll print our function. Now we are ready to print our function. And we'll see if it works. Yes. Our algorithm has been able to locate the minimum for the function. For sphere function, the objective function value is located at 0, 0, 0. The sphere function has the lowest value at 0 and its global minimum is at 0. Okay, so I'll type the value of g best for you. It's very close to 0 in this case. This objective function value is the global best is our best estimate for the minimum. Any questions for in the code? So you can try out other functions in a similar manner. I can show you, like, see, generally we running it once. This time our function has been able to secure the global minima, but generally people want to try it out for a number of times. Okay, so this time we had it only once. Our dimension was 30 and we chose sphere function. You can choose some other function like actually. Let us see how well our algorithm does on Ackley function. I modified the parameters for Ackley function. Okay, that's also figured out for Ackley. It's getting 0. Yeah. Any questions? Okay, so we'll try out this program with other and compare with other algorithms. Suppose I have written a PSO code for Rosenbrock function, and I'm running the code for around say 21 trials, meaning I'm running the code repeatedly for 21 times, and I'm seeing how best the function is optimizing. Okay, so we are running for Rosenbrock, and you can see that the functions as a start emerge, the best the PSO that we wrote can do for 300,000 functional evaluations is only this much. Okay? This is the best minima that it can give, but yeah, it's not so great, but this is the best it can achieve. So I have asked the program to run for 21 trials. Okay, so our output is of the order of 10 to the power 6 for most of the trials. So all our output is too high. Let us. This is another algorithm called galactic swarm optimization, which I developed as for my PhD thesis. I would like to show you this algorithm, how this algorithm does in comparison with the regular PSO. So the a regular PSO gives an output of 5 into 10 to the power 6 or so. The best it can do is only about 3.5 into 10 to the power 6, not so great. Let us run the galactic swarm optimization algorithm, which is a variant of particle swarm optimization. So there are 21 trials. Each trial has 5 epochs. Okay. When you see the result, you can clearly see that it is significantly improved. Okay. Here it is how in PSO it is about 10 to the power 6. Now it is way too better. You get to see even 10 to the power minus 5. Yeah. Now you can see that this algorithm is optimizing very powerfully. You get values like 10 to the power minus 5, whereas the previous algorithm gave only values of 10 to the power 6. So this algorithm is clearly superior over the previous algorithm. Any questions that you might have? You can see the statistical values. They are far better compared with the regular PSO that we have written just now. Okay. I want to say one thing. So I have shown comparison of two algorithms. One of them is the PSO, that was the original particle swarm optimization. And the other algorithm that I showed you is my development, that is galactic swarm optimization, GSO. And I said GSO is better than PSO. See, when you compare two algorithms, you need to be careful a little bit. Yeah. Actually, uh, in 1995, they released an IEEE paper by Wolfram and McCready. Okay, according to these two mathematicians, because computers generate only random numbers, pseudo-random numbers, you cannot claim that if an algorithm does better over certain functions, you cannot claim that this algorithm will be the best algorithm. Okay, you can never figure out an algorithm which you can claim as to be having more superior performance over all the other algorithms. Okay, that is because if according to their theorem, that is called no free lunch theorem. What they said, if you have two algorithms, let us say GSO and PSO, in this case, if GSO does well on, say, some subset of function space. Okay, let us say that you can imagine all types of functions. Okay, if GSO does well on certain categories of functions, it will turn out that PSO will do better on the remaining category of functions. Okay. So you cannot make a universal claim that you have found out an algorithm and that is superior over all the other algorithms. That cannot be claimed. So the problem is you have to know something about the function that you are optimizing. Okay. So let us say that in this case, I have shown my algorithm GSO that is doing better. How can I claim that it is a superior algorithm? Is based on practical considerations. Okay. Suppose GSO, the galactic swarm optimization, does consistently well on practical problems. Like you might take it to be any cost function that you find out for your application in electrical engineering also or like that. So, and if for all practical functions GSO does better over PSO, GSO's performance is better over PSO in the space of practically useful functions, then GSO is worth consideration, and it is more effort can be put into the when you compare two algorithms, you have to keep in mind the practical functions that come in your application, and depending upon the type of function that you have, one algorithm could outdo the other algorithm. But you will never be able to figure out or construct an algorithm that outdoes other algorithm on every function. That is what no free lunch theorem says. Any questions?
Yes, participants, we want to ask questions regarding PSO, particles form optimization. Sir has wonderfully demonstrated how that algorithm works in MATLAB environment. Yes, participants, please come forward and ask if you are having any kind of query.
Good afternoon, sir.
I have one
Tell me,
doubt.
sir.
May I ask you?
Yes, madam.
Yes,
Hello.
Subhash Anukar, sir. Yes, sir.
Yes, yes. Can I develop the algorithm for DGA test, dissolved gas analysis, to optimize the function? That how can I develop the function if I have a DGA result having hydrogen, carbon monoxide, methane, then
Okay.
ethylene, ethane, acetylene? Then how can I develop this algorithm in the MATLAB? And you have explained very well,
Sir,
but the
okay, my suggestion is
program is very large. We cannot understood one single page. So if you elaborate that in different file, then we can understood very easily. This is my suggestion.
sir, actually, in your case, what I would suggest, there are some existing algorithms. Okay, the field of heuristic algorithms, they are proposing so many algorithms, and I don't think it is unless you do research in a PSO or GSO, you can construct an algorithm. What I recommend is you can download an algorithm and you apply it for your case. The one thing you have to do is formulate your problem as a mathematical function. Okay. Once you have done that, every algorithm is identical.
But
You just have to
my question is that
uh,
how to understand the downloaded algorithm? It is very task. It is very big task to understood and the algorithm which is downloaded from them.
no, you don't have to understand. Why are you trying to understand? So actually, in this particular problem also, I took the particle sum optimization. I took one function like sphere or Rosenbrock. Okay, uh, you have to figure out a way to formalize your function as a mathematical equation, and once you have that function, you just input it to the algorithm, and the output it will give the optimum value. If you try to understand all the algorithms that are available, that are presently being researched and they've been done, I don't think it's practically possible for all of us to understand every algorithm and then try to apply in our case. See, we are primarily looking for algorithms that we can apply. We have to develop the skill of applying algorithms rather than trying to understand it.
Okay, sir. Thank you very much.
Yeah, that is what I would suggest.
Yes, any questions from participants? That means, sir, problem formulation, it is the main step for application of any kind of algorithm.
Yes. If you were able to formulate your problem, then you apply. Any algorithm is equally good. Like unless you test it, and you find out which algorithm is giving better results for you, then you can go ahead with the publication. That is what I would suggest anyone who is using meta-heuristic algorithms for their problems. This is, I think, it's a practical, sound advice. Okay. Please don't try and understand all the algorithms. Well, if you can understand it is good, but algorithm synthesis and writing algorithms and developing algorithms is different task, different research area compared to applying it for your problem. You have to see how people have applied algorithms for your specific problem, and then you have to borrow those ideas and use a new algorithm and see if it is giving better results.
Right, sir, right. Sir, as you explained here about the particle sum optimization in MATLAB environment for certain benchmark problems.
Yes,
Sir, for like sphere, Rosenberg, Ackley problem, benchmark problems. Sir,
yes,
for
madam.
PSO, for writing code for PSO in MATLAB environment, first we have to, as you have shown there, address to the function, that is function Ackley or function sphere. So
Yes.
how to write or how to call them in main PSO program?
PSO program. Yeah, that's
Suppose
what.
if we consider for sphere,
Okay.
huh,
Madam, like, okay. See, in this case, I'm using Rosenbrock function. Can you see my screen? Can you see my MATLAB?
yes sir,
Yeah. You only need to give your command, this command, and you have to give xmin and xmax for this GSO, correct exponent optimization that we developed. If you say f equal to @Rosenbrock, then what MATLAB will do, it will start searching in the same folder whether there's a Rosenbrock function defined. Actually, I have given a Rosenbrock function in the same folder. Okay, then it will look for that function. I think, yeah, the function is also here. This is a Rosenbrock function.
yes sir, yes sir.
Yeah, that particular function must be in the same folder in which you have the optimizing algorithm.
Right sir, got it sir.
Yeah. Then you can simply invoke this command f is equal to @Rosenbrock. Then every time you use f within brackets, it will evaluate Rosenbrock function. That's what it does. See, here I am not using Rosenbrock within brackets f. Instead of that, I am using f within brackets.
Yes sir. Okay, thank you sir. So I think today's session we may conclude. Yes,
Yes.
participants, do you have any queries? Okay, sir. So tomorrow, sir, we will be meeting on same time with GSO, sir. You are going to explain us GSO about GSO.
Yes, madam. I'll try to introduce some applications of that and how to compare two algorithms for if you are using, say, any applications you have. First, I will use benchmarks. Then I'll try to find out some applications, and maybe you can try working on that.
Yes, sir. That will be
Yeah, more
helpful.
applicable for. Yeah.
Because comparative study is always needed. That how the
Yeah.
GSO is better than PSO, that one can must understand. So that will be more useful session, sir. So
Yes, ma'am.
thank you, sir. Yes, thank you, sir. You had given very really wonderful hands-on session on particle sum optimization. We are really thankful to you, sir, and also for all our participants. So, dear participants, attendance link and feedback link has been posted in your chat box. So, please fill that. Tomorrow, we are going to meet on same time with Venkataraman sir for another wonderful and interesting session for the comparative study of PSO and GSO. So, thank you very much, sir. Thank you for your wonderful guidance on this meta-heuristic algorithm. Thank you very much, sir.
Thank you, madam.
With this, the permission of